Alright, the purpose of this activity is to introduce you to use substitution in definite integrals. And I want to use this to help you make the connection to kind of what's happening graphically when we make a use substitution. Because if we make it algebraically, then we're obviously changing the graph in some way, and we should ask the question, like, does that make sense? And so that's what we're going to explore here today. Usually I would let you puzzle over number 1 and 2, either with a partner or by yourself for a little while, but since I'm not there, we're going to go through 1 and 2 together. So you're going to use 5 GeoGebra applets today. I posted them in the assignment in Google Classroom, so you can link to them. All right. But before we even use the applets, consider the following integral. I've made this use substitution for you. What did I choose for u? Also, what are the bounds of the new integral that are written in terms of u? You can confirm this with applet number 2, which we're not going to look at, but you can take a look at it if you want to. So I've taken this integral here, 0 to pi over 2 cosine x sine x plus 2 squared, and you can see directly I don't have a rule for anti-deriving this expression directly. Okay, so I made a u substitution. I made it u squared. And if you thought about this for a little while, you could probably figure out that that means that u had to be sine x plus 1. Okay, so that had to be sine x plus 1, and that means that du, when you take the derivative of this, it's going to be cosine x dx. And you can see here in the integral, if I make this u, that will give me u squared, and then that cosine x dx right there becomes the du down here, right? So there's the substitution, but what about the bounds, right? So up here we start with the bounds from 0 to pi over 2, but it would be pretty wild if the bounds that gave you the area to this integral, right, that if those bounds were the same in the integral down here, which now has a completely different function, right? Cosine x sine x plus 1 squared is a different graph than u squared, so how do the bounds change? And the big insight here is that if you change the function by setting up this substitution here, that u is equal to sine x plus 1, then what we can do is use that to also change the bounds. These bounds up here were in terms of x, right? X equals pi over 2, x equals 0, all right? So the bounds down here are going to change. They have to be in terms of u. So what we'll do is we'll take u and evaluate it at pi over 2. Okay? And so u of pi over 2 is sine of pi over 2 plus 1. And that is just equal to, let's see, sine of pi over 2 is 1 plus 1 is 2. Okay, so that upper bound then becomes 2. All right? And then u of 0, that's what we'll do next, right? We'll go and pick up the lower bound. U of 0 is sine of 0 plus 1. That's just going to be 0 plus 1, which is 1. So the bounds go from 1 to 2. All right, so that's the big insight, is that the u substitution allows us to change the bounds. We're changing the function. We can change the bounds accordingly using that same substitution. It's kind of a linchpin to the whole thing. Right? Okay, let's go over here. Now, consider the following integral. I've made a u substitution for you. What did I choose for u? Also given the bounds, what were the bounds of the original function? So what, this one's a little different, right? In this one, I don't have the original bounds. I have the bounds for u. And so then can we figure out what the original bounds were? So if I look at my simple function here, it's square root of u. That means that this expression here, x squared plus 1, must be the u, right? So if I set u as x squared minus 1, then du would be 2x, excuse me, dx. And you can see that here, that would be du, right? So there's my u and du. And you can see that down here as well, square root of u du. Now, my bounds here, whoops, forgot the x there. My bounds here are 3 to 15. Okay, and again, this right here is what is connecting the two integrals together. So if I know that this is u equals 15 and u equals 3, then I can take and substitute u in, or like let's say 3, I guess, 3 in here, and solve for x. And then I can take 15 and substitute it in here and then solve for x. Let's do that off to the side here. So I will take, I guess we'll start with the upper bound. 15 is equal to x squared minus 1. Add 1 to both sides, I get 16 is equal to x squared. I'm going to take the square root of both sides. I could do plus or minus, but this is going to be the positive root because u is 15, so we've got to be to the positive x-axis, although that won't always necessarily be the case. We could guess and check and experiment. We'd find that it has to be 4. All right, so x is 4. That's my upper bound. All right, and then I'm going to take u is equal to 3, so 3 equals x squared minus 1. Add 1 to the other side, I get 4 equals x squared. Square root both sides, and I get x equals 2. Okay. All right, so that's my lower bound. All right, now both of these then would be in terms of x, right? X equals 2, and x equals, I'm drawing arrows, x equals 2 and 4. All right, so that's how we're going to be addressing definite integrals in u substitution. And the rest of this exploration, you're going to be looking at these graphically. Again, you're going to be using these GeoGebra applets. They're linked in the assignment in Google Classroom as well as on the lesson plans if you need to get to those links. Otherwise, that should get you started. The answer key to this is in the binder of the solution guides. And so you should check your work as you go or at the end of the activity. All right, thanks.